In this video, we will figure out how to form accurate drawings of all molecules by using the Vesper model and figure out the reasoning behind molecules geometry. This process is called molecular geometry. Molecular geometry is the three-dimensional arrangement of the atoms that constitute a molecule. In Chapter 8, Lewis structures were used to account for the formulas of covalent bonds, but they don't indicate the shapes of the molecules. For example, CCl4's Lewis structure just shows that there is 4 chlorine atoms bonded to one chlorine atom, as seen right here. One carbon atom is bonded to 4 Cl atoms. But the actual 3D arrangement of the atom is where the 4 Cl atoms are bonded to the carbon atom in the corner of a tetrahedron shape, as seen in this photo. This is a tetrahedron. It's similar to a triangular pyramid. And the bond angles, as seen right here, of each bond angle is 109.5 degrees between this bond, these bonds, these bonds, these bonds. So there are 6 bond angles total in this tetrahedron shape. When molecules with multiple atoms of the same element are bonded to one atom in the center, the common formula is ABN, as seen right here, where A is the central atom and B are the atoms that are bonded to the central atom, and N is the number of atoms that are bonded to the central atom, which is B. So, and if, for example, CCl4 would be CCl, or AB4. Common AB2 shapes are linear, as seen right here. So AB2 right here is linear and bent. Common AB3 shapes are triangular planar, which is basically if you draw a line between the ends of the B molecules, you would get a triangle, triagonal, pyramidal, and T-shaped. Although there are many shapes in molecular geometry, they can all be easily drawn because many of them are very similar. As seen in the picture, a tetrahedron-shaped molecule can be turned into a trigonal pyramidal with 3 B atoms and even a bent shape, which is right here. It is possible, however, to predict these shapes by using a Vesper model, which is right here. This stands for valence shell electron pair repulsion, but it's easier just to remember as Vesper, and that's how we will be recognizing it in this video. One way to visualize this Vesper model is to be using balloons that are connected to their ends. And using this, you can use n number of balloons, but the important thing is that they're all connected by their ends, as seen in this photograph. With 2 balloons, as you can see, it kind of represents a linear shape. With 3 balloons, it represents a trigonal planar. And with 4, it represents a tetrahedral orientation. Each balloon can represent an area that is called the electron domain, which is the area occupied by electrons between the 2 atoms. The electron domain represents a bonding pair of electrons, but it also represents a non-bonding pair of electrons, which can be seen in NH3 right here. So NH3, when you draw the Lewis structure, has 1 pair of lone electrons. So this bond, and this bond represents a bonding pair of electron domains. But this is also an electron domain. It's just called a non-bonding pair. In a normal molecule that follows the octet rule, there will only be 4 electron domains, as seen right here, 1, 2, 3, 4. But in molecules such as SF6 or PCl5, there will actually be 5 in this one and 6 electron domains in that one. So that is why when you're approaching solving a molecular geometry problem, it is the first step that you should take is to find how many electron domains there are. And the easiest way to do this is by drawing the Lewis structure of the atom. So, for example, how many electron domains does a molecule like H2O have? If you said that H2O has 2 bonding domains, then you would be wrong. That means you didn't draw out the Lewis structure. When you draw out the Lewis structure, you get 2 bonding domains, but you also have 2 lone pairs, which means that there are 2 non-bonding domains. So that totals with 4 electron domains. The Vesper model is based off how electrons are negative, and therefore the electrons of an atom will repel against the electrons of another. An atom will be as far away from the other atoms. But the bonding atom will stay equidistant from the central atom because the bond distance will always be the same. It is helpful to go back to the balloon example to figure this out. If you have 2 balloons connected, then they will be as far away from each other, so it will be a linear shape. Same thing with 3 balloons, 4 balloons, 5 balloons, and 6 balloons. So balloons represent electron domains. So if we go back to the Vesper model, it is based off how electrons are negative, and therefore the electron of an atom will repel against the electrons of another, and the atom will stay as far away from each other. But the bonding atom will stay equidistant from the central atom because the bond lengths will always stay the same. It is helpful to go back to the balloon example to figure this out. If you have 2 balloons connected, they will stay as far away from each other as possible. Same thing with 3 balloons, 4 balloons, 5 balloons, and even 6 balloons. This is exactly what happens to molecular shapes, and each balloon represents the electron domain. So when approaching how to solve a molecular geometry problem, think of the electron domains as balloons, and they will repel each other completely. This is why finding out how many electron domains a molecule has is so important in this process. When taking the AP exam, one common question is what is the bond angle of this molecule? An easy way to solve this is figuring out how many electron domains the molecule has, and once that is figured out, you can use this basic principle. As seen in the photo, if a molecule has 2 electron domains, the ideal bond angle will be 108 degrees, and will rarely stray away from that. If a molecule has 3 electron domains, the ideal bond angle will be 120 degrees. With 4 electron domains, the ideal bond angle between each bond is 109.5 degrees. Now, when you get to electron domains of 5 electron domains, the angles get trickier, whereas some of them will be 90 and some of them will be 120. But this is a rare question, and this will not be asked in the AP exam. When going to up to 6 domains, every single angle for an ideal angle will be 90 degrees. Now, using this knowledge, what would be the bond angle of a molecule with 4 electron domains? It is very important to memorize these values because they will most assuredly be tested on the AP exam. So now we can start to see a 3-step process for finding the molecular geometry of a molecule. The first step is easy. You just have to draw the Lewis structure. The next step is you have to find how many electron domains the molecule has. In ammonia's case, as in this picture, there are 4. It is important to remember that a single bond, a double bond, and a triple bond, and a non-bonding pair all count as 1 electron domain. The next step is to determine the angle of the bonds. In an ammonia case, it is 109.5. So, once you remember that, you can figure out that it looks like a triangular pyramid. And if you take away the non-bonding pair, the shape of the molecule will be a trigonal pyramidal. Now the actual bond angles of ammonia will be less than the ideal 109.5 degrees because the non-bonding pair in ammonia will always repel the other bonding pairs more, which means that the angles between the bonding pair will be less than the ideal value. The same thing happens with double and triple bonds, where they repel the single bond domains away as a result, decreasing. So, in ammonia's case, the angle measurement will be a little bit less than 109.5 degrees just because of the non-bonding pair. But in an H2O molecule, it will be even less than the ammonia's pair because it has 2 non-bonding pairs. But in a molecule like ammonium, which is NH4, it will and has 4 bonding domains, that will be the ideal amount, which is 109.5 degrees per bond angle. So now that you have learned about electron domains, it is now time to learn the names of the shapes. And it is always helpful to have a good chart with you. So, if you have 2 electron domains, they will always be bonding domains, so it will always be a linear shape, so 180 degrees. An example of this is CO2. If you have 3 electron domains and all of the domains are bonding domains, then it will be trigonal planar. An example of this is BF3 because B does not follow the octet rule. If you have 2 bonding domains and 1 non-bonding domain, however, it will be bent. As an example of that is NO2. If you have 4 electron domains and all of them are bonding domains, then the shape will be tetrahedral, which I have been referencing multiple times throughout this video. If you have 3 bonding domains and 1 non-bonding domain, then the shape will be trigonal pyramidal, just like NH3. And if it has 2 bonding domains and 2 non-bonding domains, the shape will be bent, just like in the with 3 bonding domains. But if you have 5 bonding domains and 0 non-bonding domains, then the shape will be trigonal bipyramidal, and that's the one with the weird angles with 90 and 120 degrees. An example of that is PCl5. If you have 4 bonding domains and 1 non-bonding domain, then the shape will be a seesaw shape. If you have 3 bonding domains and 2 non-bonding domains, it will be a T-shaped, which example is ClF3. And if you have 2 bonding domains and 3 non-bonding domains, the shape will be linear. And finally, with the octahedral, if you have 6 bonding domains and 0 non-bonding domains, the shape will be octahedral, and that an example of that is SF6. If you have 5 bonding domains and 1 non-bonding domain, then the shape will be square pyramidal. And finally, if you have 4 bonding domains and 2 non-bonding domains, the shape will be square planar. Now that you have been introduced to all the molecular geometry names and how many bonding domains and non-bonding domains Now that you have been introduced to all the molecular geometry names, how many bonding domains and non-bonding domains does the trigonal pyramidal molecule have? Although so far we've only been applying this to molecules that all center around one central atom, it is possible to find the bond angles of a molecule with multiple central atoms. For example, the molecule CH3CO2H has a very complex Lewis structure, but it is easy to find the bond angles for the hydrogen carbon-carbon bond by drawing the Lewis structure and then figuring out the molecular geometry, which then leads to the bond angle. So the first step is always to draw the Lewis structure. So the Lewis structure is the central atom, which is C, bonded to 3 hydrogen, bonded to another carbon. This is bonded to oxygen, and 1 hydrogen. So the hydrogen carbon-carbon bond is right here. So we need to figure out the molecular geometry of this carbon atom. And because it has 4 electron domains and all of them are bonding domains, that means the shape is a tetrahedral shape. Now that we know it's tetrahedral, that means we know that each angle is going to be 109.5 degrees. So that includes this hydrogen carbon-carbon angle. So that is how you figure out how to find the angle of a complex molecular structure. Another example that we can do is predict the molecular geometry of a molecule SnCl minus, Cl3 minus. So the first step is always to draw the Lewis structure, which is Sn surrounded by 3 Cl molecules and a lone pair. So we know that it has 3 bonding domains and 1 non-bonding domain, totaling with 4 electron domains. And with 3 bonding and 1 non-bonding, we know that the shape is trigonal pyramidal. Which we can see in our chart right here. So the last example that we'll do is find the molecular geometry, and B, the bond angle of the molecule O3. So first step is always draw the Lewis structure, and with O3 it is a resonant structure, so it can also be this. So we know that but it stays the same throughout with a resonant structure. So we know that it has two bonding domains and 1 non-bonding domain. So that means that totals 3 electron domains and then 2 and 1. So that shape corresponds to the bent shape. So the molecular geometry of O3 is bent. And that's the answer to A. Now B is we use the molecular geometry to figure out the angle. An angle on a normal 3 electron domain molecule is 120 degrees, but this is not normal. We have both a lone pair and a double bond to this O. So the angle will be much less than 120 degrees. Sorry. So it would be much less than 120 degrees. So now that you have learned to effectively use electron domains to find the molecular geometry of a molecule, find the molecular geometry of ClF3. If you have been paying attention, you should now be able to figure out the molecular geometry of a molecule with one central atom. Find the approximate angle formed by all molecules, and also reasoning behind all of this. My name is Charlie Schaefer, and thanks for watching. I hope this helped. If it was helpful, please subscribe to my channel at Charlie Schaefer 19 if you want to receive no more videos on chemistry, or really anything for that matter. Unless I have to do another project. If you have any other questions, don't email me, call me, or fax me, or text me, but instead ask Mr. Pulliam your question. Thank you.